environmental coating. Coating is a covering that is applied to the surface of an object, usually referred to as the substrate, to decorative, functional, or both to protect assets from environmental corrosion, in order to provide a long service life. Not only avoid corrosion, but it has a real and detrimental effect on costs to the asset owner in terms of service time, downtime, performance levels, and ultimately, asset value. The coating system must be compatible with the component's base material in order to protect against environmental attack and to prevent degradation caused by the coating itself. So, the coating must be environmental friendly with very low or zero risk and solutions for the prevention and remediation of hazardous materials, molds, viruses, and bacterial. Parylene is the trade name for a variety of chemical vapor deposited polyphenylene polymers used as moisture and dielectric barriers. Parylene is green polymer chemistry. It is self-initiated, no initiator needed, and unterminated, no termination group needed, with no solvent or catalyst required. Parylene has become the protective coating of choice for challenging electronics, aerospace, and medical applications. Conformal coatings are generally liquid in nature, while parylene is formed on surfaces from a high-purity powder known as a dimer with no liquid stage. The resulting film is thin and conformal, has no pinholes, and resists the effects of organic solvents, inorganic reagents, and acids. Parylene properties and variants. First, Parylene N. Parylene N has the highest dielectric strength of the three versions, and a dielectric constant value independent of frequency. It is able to penetrate crevices more effectively than the other two versions because of the higher level of molecular activity that occurs during deposition. Parylene N is commonly used in high-frequency applications because of its low dissipation factor and dielectric constant values. Second types of parylene is Parylene C. Parylene C differs chemically, having a chlorine atom on the benzene ring that results in a useful combination of electrical and physical properties, including particularly low moisture and gas permeability. This version deposits on substrates faster than Parylene N, with a consequent reduction in crevice penetration activity. Third is Parylene D. Parylene D has two chlorine atoms added to the benzene ring. This gives the resulting film greater thermal stability than either Parylene N or C. It has reduced ability to penetrate crevices compared to Parylenes N and C. The last one is Parylene types HT. Parylene HT, the newest commercially available variant of parylene, replaces the alpha hydrogen atom of the N-dimer with fluorine. This variant of parylene is useful in high-temperature applications, short-term up to 450 degrees Celsius, and those in which long-term UV stability is required. Parylene HT also has the lowest coefficient of friction and dielectric constant, and the highest penetrating ability of the four variants. Value of parylene conformal coating. A polyparylene coating film is a conformal protective polymer coating which formed by the chemical vapor deposition (CVD) process. This method of application yields a true conformal film complexion that contours all surfaces, exposed or hidden. Moreover, it protects any component configuration on such diverse substrates as metal, glass, paper, resin, plastic, ceramic, ferrite, and silicon. Usages for the parylene coating includes implantable devices, fish tags, circuit boards, SMT, through-hole or mixed technology, sonar applications, ultrasonic applications, surgical devices, and elastomers. Parylene coating is a high molecular weight, linear, crystalline polymer having an all-carbon backbone without any oxygen, nitrogen, or sulfur atom links in the backbone. It is hydrophobic. This carbon backbone, coupled with its substantial crystallinity, makes parylene quite stable and highly resistant to chemical attack. Process of parylene. Parylenes are formed at around 0.1 torr. Under these conditions, the mean free path of the gas molecules in the deposition chamber is in the order of 0.1 centimeters. Therefore, the deposition is not line of sight and all sides of an object to be encapsulated are uniformly impinged by the gaseous monomer. This is responsible for the truly conformal nature of the coating. The process consists of three distinct steps as shown.